What we will do today, we are going to start with generative methods, and we are going to see the k-means algorithm. Now, when we talk about k-means, it's a segmentation algorithm. Like I was showing you when we were brainstorming, there is a set of answers given one question, and I was forming different segments based on that. So for each set of elements, I was putting them together. This process that I was doing is called segmentation in computer science. So what I'm going to try to do this time is that I am going to show you different terminologies, because when it comes to data science or AI, many people are sitting at the same table from different expertise. So we find statisticians, so here they call it unsupervised learning, and it's the same thing, it's segmentation. If, for example, I find psychiatristics, they call it sorting, and it's the same thing, it is segmentation. And people from data mining background, they call it segmentation, and it is segmentation. So if you may listen the same term, or if you're coming up through one article, you'll find unsupervised learning, they're talking about segmentation. You find sorting, it's the same thing. So here you try to just keep in mind that sometimes we talk about the same thing, we all mean the same thing, but we are just using different terminology, okay? It's synonyms. So what is it in all cases? This is unsupervised task. So segmentation is a task of unsupervised learning that aims at forming homogeneous groups of shapes. When we say homogeneous, we are going to see this in details, means things that having common characteristics, okay? So once the groups are formed, other techniques or expertise must uncover their semantic meaning and potential significance, which means it's not enough that I was here, for example, making or performing a segmentation task. It's not enough that I'm saying, okay, all this belongs to some cluster I'm going to call data, all this belongs to something related to models, and this, for example, application, I don't know what. Beyond this, I was adding something, which is discussion. We are putting all the puzzles together. We are exploring what's beyond this cluster. So, and as I was telling you last time, machine learning, data science, AI, or whatever, it's not just about performing a given task. It's more than that. It's not only turning data into information, but from that information, we need to take decision. We need to have influence on the real world, okay? So this is what we are just saying right here. And once we are making potential significance, means it's not enough that someone is coming, I'm going to say man or woman. I need to, based on that, there is something to do. If, for example, man, and it's a context of marketing, for example, I'm going to show him a set of winter coats, for example, designed for men. If it's a woman, I have a set of new cosmetic products, for example, which is designed for this specific, I'm going to call it market segment, okay? So the applications here include marketing, this is what I was just saying, which is to discover or form groups or categories of customers and design well-suited marketing approaches, which goes beyond clustering. This is going to give impact, whether societal impact on finance or whatever. We want to see the real change, the real impact of these machine learning algorithms. It's not like we are just performing them. In information retrieval, here we segment large databases into homogeneous groups of smaller size to accelerate information retrieval. Let's suppose you are on Facebook and you are going to search. So this is information retrieval. You are looking for something to get some information. Now, there is not only to search for friends and messages and a particular word in a given message and posts, and there is a space where you search in your own messages, space where you search for people, space where you search for posts and so on, okay? So this is how we are putting categories, and you can search in your particular category to make it faster, okay? It's also useful in urban planning and banks and finance. And in real life, like for example, in this example, what you can see here. Okay, so these are Simpsons. Everyone knows them. And if I'm going to ask you that you are going to perform some segmentation or to form some groups, given this, like Simpson. So what categories or groups you may suggest?
Based on the work.
Yeah.
Based on what they work, like the entire.
Okay, this is possible.
Family members.
This is also possible. So what does it show? We can like form them in groups of the Simpson family members and others belong to the employees, okay? Or we can have a group of men and women. So this shows what? This shows that segmentation is subjective. So for you, and given the same data now, each could have his own criteria. So I cannot say that she is wrong. I cannot say that you are wrong. I cannot say, but it depends on the context that what like clusters or what groups we are going to form. Is that clear? Okay, now what we will do is that we are going to move through basic definition of this, what we are performing now, which is segmentation, to how it's really done. So clustering, or when it comes to segmentation, clustering is the segmentation of data given, like if we need to organize them, for different groups. What we will use here, what we will use is the similarity. As we see in the employees group, there is a similarity, which are employees, and others family members, they have some similarity criteria as well, or in the other case. So people or elements or samples or examples that are belonging at the same class or the same group are similar and to each other, okay? And they are dissimilar to those from the other group. So the Simpson family are similar and they are different from employees group. Or women are similar and they are also different or dissimilar from the men group. It's like this. So the main criteria to define a cluster is a set of elements where there is similarity given the shapes or elements from the same group among themselves, and dissimilarity to other shapes belonging to other groups. Is that clear for everyone? Okay, now this is the case, for example, how could we decide how are we going to form these groups? So we can see that, for example, here, these elements are having some characteristics that distinguish them from these elements. Like, for example, I'm going to check the interval of, given the axis, for example, for this like set, I'm going to find it belonging to a specific interval, and if I'm going to, so you see this group, if I'm going to project now, I'm going to check the X elements. It's going to be, for example, between 1 and 3. And for this group, it's going to have the X varying from 5, let's see, to 9, which is making these elements having different like characteristics than this one. Now, given the Y axis, for example, I can find these are different from these. Okay, so each time there is a like difference that is making this cluster different from this cluster, this one, and this one. Is that clear? Okay. So a good clustering method now, it must ensures a high intra-group similarity, which means elements from the same group must be that much similar that we do not distinguish between them. There is that much high intra-group similarity. And if we compare them to elements from other groups, there must be that low intra-group similarity, okay? Like this, we are having a good clustering method. Otherwise, if I have elements which are very near, given the X and Y coordinates, let's say, it will be very difficult to distinguish them, okay? Now, what we have here, so some questions could be raised. What shapes are considered? How are they represented, or how to represent things? And we are already going through the knowledge representation part. We're going to focus more on this point. And what similarity measure should be used? Like when we were like forming groups given the Simpson family, it's you who decided things. But if I want to really measure, this is a new sample is coming. It's like, for example, it's the family or the employee. Probably one measure could be the DNA, for example. Okay, so I need accurate measures in this case. And what measures of cluster quality? Okay, now once everything is okay, how would I say that it's final? This cluster is really representative. It is the final one. I'm not going to like tune any hyperparameters or anything. Okay, so this is an example that may motivate you. For example, if I have in the in the net and I have images, so I can search given, I can cluster the existing information on the net given its type. So the data itself could be a possible way. These are images. I have a different representation of what could like give me a different cluster. These are web pages. I can have like here tables, okay, and I can have, which are already images, but it's different from these ones. So these are real world images. These are handwritten digits images. So it depends on the data set itself. We could form some clusters as well. So many factors are there, and we need to have exact and accurate measures, and it's not a typical problem. So clustering can make you, like, for example, decide which groups are similar. You can maybe find some similarity between these two data types, which are at the end images, okay? These are web pages, and these are, for example, different type of data. Now, what we have, it shapes and knowledge representation. Now, let's go more like near to the representation of things. I have that chair I have been always talking about. Now, how to represent that? It's a shape at the end. And a shape, I could represent it by a variable I'm going to call y, for example, for a particular shape. Or for example, x is something, okay? So y is a given shape. It's a simple thing. So this y, which is a shape, having some hidden state or hidden like characteristics, which are the class. The class means the label for this thing. For example, that shape, the class is what? It's a chair. Okay, so if I have labeled thing for this classroom, I have tables, chairs, computers, and this is the class. Okay, for that, like chair, which is the shape given by y, and having a hidden state, we can have additional information about it, which is about the semantic meaning or an explanation. What is that exactly? We can, so for a given shape, we can have a long list of hidden states, which has additional information about that given shape, okay? Now, how to represent all that? And to represent things, we always use the tool, which is maths. So if you have your shape, you can represent it with a number of attributes, okay? So the class could be like one attribute, or for example, the color could be one attribute, the height, one attribute, dimensions, I don't know, whatever, like possible. And for additional information to describe a given shape or a given thing, it's called like its vector, represent its attribute, observation or primitive vector. So here we come back to the same point from where we started. There are different names for the same thing. So someone called the vector of features, sometimes called the vector of attributes, sometimes someone called the vector of primitives, so someone called the vector of observations. At the end, it is the same thing, is the vector, like encoding all the values of the informations that are describing the given shape y, okay? So we denote that, for example, this feature vector is x, and x is having like sub-informations about x1, x2, and xn, where n is the number of observations or samples of our attributes or whatever. Is that clear? Now, we are learning about representation. This now we are going to have, is it going to be like this vector x? In this case, we say that we are encoding it, one of the additional information is it's a chair. But in this case, the chair is the class, which is the final label for that, which we don't have, we suppose. If we do not have the label, okay, we are going to store like this is something, color black, I don't know, dimensions, this and that, and I don't know that it's a chair. So I am going to store this in unlabeled data set. And in this context, I am in which case of learning? Unsupervised learning. Now, what is the difference between that and the supervised learning?
The output is predictable at the supervised, and unsupervised, like we have.
No, we are discussing still not about the output. Given the data, this y, this feature vector, or this vector of attributes, now it's having all the attributes, and I don't know about that thing, what is it? So this is unlabeled data. When is going to be labeled data?
We add the y.
We add the y. It's not in this vector. So somewhere here you might find the description, it's a chair. I am going to say this is not supervised data. There must be a separate, like, given scalar or additional value or a vector or whatever that is going to encode this information about the label. So there is a separate, or other than that vector of attributes, we are going to have the y, which is the label, okay? So in this case, we are having labeled data set, which is going to prepare us for a supervised learning, okay? So a cluster now is represented by one or more centroids. Now we have the mathematical background. You're going to come back for that. But what we say in segmentation, we are going to form different clusters. And different clusters for what? For our data, which could be supervised or unsupervised. Now, once we have data, we have information, we have the mathematical like way it's how it's encoded, how things or variables, what does they really represent. Now we are going to define what is a cluster. So a cluster is represented by one or more centroids. So there is a keyword here. What is a centroid? Centroid, it's a prototype or a reference shape. So if, for example, I say woman, it comes to my brain, for example, someone with long hair, with a dress or something like this, okay? If I say like family Simpson, it comes for me a different way of dressing or a different, like a way they're looking maybe similar or a color or something. Some features that are going to make me decide it's a reference shape, which if given a new element, I'm going to see the similarity or not between this reference, okay? So now what we will see here, for example, we are having a set of points, okay? And if we want to like decide how many clusters are there, these are represented by plus symbol, for example. And these are represented by circles. Let me specify things. Because it's a reference shape, it must have accurate information. So it's a red circle and a blue plus, okay? So this is going to be one centroid and this is another centroid. Is this clear? So this is how, given data, you are going to decide how many centroids are you having. This is coming from the fact of, if I have these shapes, I'm going to take how many reference shapes. So in this case, I'm taking 2, and this is how I am deciding that there are 2 centroids, okay? Now, if next time there is a new element coming to this 2D space, I want to decide if it is belonging to this centroid representing, or the representative of the blue plus, or to this part, or to this centroid, the representative of the red circles. How can I decide? Yeah, which means, yeah, I'm going to measure the distance and see if it's closer or not. But can I do this all the time? This is somehow in the algorithm to do this. But at the end, let's see things from far. What is our main objective? If I have this set, and I'm already creating 2 centroids, and at the end, my main objective is, given the whole space, what I want to do are my clusters. I'm already forming these 2 clusters. We can see clearly, this is cluster 1, represented by centroid, let me say 1, and this is the second cluster represented by centroid 2. Let's see how I am doing this. If anyone is coming, I'm going to check the distance, check the distance, check the distance. But let's see things.
The clusters may change.
Whatever the clusters, okay, yes, clusters may change, and they do change, but at the end they converge to given fixed position. Let's suppose that we are in the perfect case. This is the fixed position for each cluster. The main objective, if I have a 2D space, and in the reality we have a bigger space, what is the main objective of performing this or doing this? It's when a new element is entering, someone is coming to the class, we are going to decide. This is what we will do exactly. Now, how to decide?
The color and the shape.
The color of the shape, these are characteristics. They are prototype, which is helping us to create the prototype or the representative of the shapes. And it's there, and it's called the centroid, and it's there. And we are having one centroid, which is there, one is there. So our space, which is the huge space, is having 2 centroids, which means what? Which means that our space is divided into 2 subspaces. And this is where we do use it, segmentation. It's not only about deciding, okay, these are plus and these are circles. One new element is coming, but it's here, so I'm going to say this is a blue plus. Up, it's here, I'm going to say this is a red circle. Okay, so this is going to give you a final, let me say, division of the space into 2 subclasses. And what do we call this? Like green line. It's the boundary between the 2 elements, which is in maths called the linear decision surface. So it's based on this surface. If next time one element is coming, we are going to decide if it's, let's say, it's exactly when we have, I don't know. For example, if you have, I don't know what example I may give, but let's suppose this is a gang, and this is another gang, and they are defining their separation. And this, if you are coming here, it's like you are in our zone, and if you are there, others are saying you are in our zone. So it's based on this. It's not only like I have a new element. I am creating this linear decision surface, which is going to give me more accurate. It's like a model. If next time an element is coming, we are going to have, it's mainly the probability that it belongs to the blue or red, let me say, group. However, you can find here these red elements. They are just here, and that's okay. You can find sometimes blue elements, they are here, and this is happening, like Ayub said, on the border, okay? We will see this problem later. Okay, so now the surface could be divided if, for example, here we have the case of like how many clusters?
Looks like 4.
Sorry?
4? You got 4 dots?
And okay, when we were defining a cluster, it is represented by one or more centroids. So in this case, how many centroids for the triangle type?
I see. Yeah.
We have 3 here, okay? So it is possible that I'm going to represent a given centroid with more than a given cluster, sorry, with more than one centroid. However, for this one, it's enough to have one only, okay? It's possible. Now, how we are doing this? In the start, I am going to suppose the red and let's say this one, okay, the blue centroid. I'm going to suppose that I am going only to have one linear line, like you see this one, which is going to separate both of them, okay? And so this is going to create for me this frontier that I'm getting, okay? Next, I am having this one, and I'm going to check also the distance given the left one and the right one. And each time I'm going to create one line, okay? And each time I am going to do the same between, for example, this red and blue. This is the green line. Between this one and this one is this green line. And at the end, before we had the example when this like surface of deciding is linear, which is straight. However, in this case, when we are having multiple centroids, is it still linear? So it is not linear, okay? It is like a composition of segments, okay? And this is how it happens. Is this clear? Okay, so what we will take from here, the boundaries, like Ayub is saying, it could be whether linear when it's a line, or it could be also non-linear, okay, when it's not a straight line. Okay, this is another example. Here we have how many clusters you can see? 5. And how many centroids per cluster? Each one is represented by only one centroid, and it's very simple, okay? So here also, the decision, okay, here we are dividing the space into 5 regions, I'm going to say. And so to divide into 5, we are not using a linear like function, okay? It's non-linear. This is what I want to say. Now, we are going to go through some concepts. We are familiar with what does a shape mean, or a form, and what are attributes. So a shape is having attributes like x1, x2, until xn, and they are, we said, like observations, attributes, primitives, okay? And this shape is also, could be called, patterns, data, instance. It has many example, case, fact. It has many other names, okay? And what we will do here is like also attributes could be having different like names, like characteristics, like for example, variables, descriptors, and so on. So don't feel confused if you see this. However, what we see for attributes, they all belong to what we call omega, which is the set of forms, and omega, which is here having different value varying from x1 to xn. Each of these values belong to a subset of this omega. For example, x1 belongs to omega 1, x2 omega 2, until we have xn belongs to omega n. Together, these all spaces or subsets of attributes, they form the whole omega that includes all of them, okay? And this will take us, if I have, I would come back to the same example of the shape, which is the chair, okay? And we don't know the label, because if you can see here, I don't have any additional information about the y, okay? So if I have my chair and it's having x1 could be like one attribute, for example, about dimension or height, for example, could be 1 point something. weight, could be, I don't know. So these are numbers. If I say height or weight, or so these numbers are like quantitative, so which gives the quantity, which in general measures like some called quantitative variables. Sometimes I am talking about what type of, for example, is a leather or some. So if I'm deciding about the quality, I'm talking about the qualitative things, which is not numerical attributes, let's say. And in the particular case of qualitative attribute values here, we have different types, starting from the nominal attributes, where the values are like the elements, the attributes are given by names or samples. So this is, for example, if I have the weather different attributes, it could be sunny, which is a name, rainy, snowy, or whatever. Okay. Now, in between this set of samples or values, there is supposed to be no relationship. I cannot measure the distance between sunny and snowy, for example. It's not possible because these are nominal attributes. And also, there is no relationship of order that is existing between such values, okay? And so one of the examples, what we can do given this, I have this information. I can only perform like equality tests, which means like if it is equal to something, then I will perform some rule. Like, for example, if weather equal to rainy, then there is no match, okay? Is it clear? So the attributes that could be stored given the list of primitives or attributes for a given shape x in the vector or y in the vector x, they could be whether qualitative or quantitative. If they are qualitative, then there is a possibility that they could be nominal attributes. And this is an example of them. For nominal attributes, the most important thing is that only equality tests are allowed, okay? Or possible. And next, we have still in the same type of qualitative attributes, the ordinal attributes, which means they are still qualitative, means they are not numbers, okay? But at the other hand, there is a relationship of order between these, even they are not numbers. If, for example, I give you the temperature, I have it could be hot, cold, or moderate. So what I can say, I can say that hot is strictly superior than moderate, which is strictly superior than cold, which makes sense, okay? So, and this also allows us to write or perform tests like if the temperature is strictly superior than cold, which means it is whether hot or moderated, then there will be a match, okay? And this is so particular in the case of Boolean attributes. Now let's move to this example, okay? What we are doing is that we are performing what we say clustering, or we are regrouping elements to those who are similar to each other and dissimilar from other groups, okay? And how to decide if I have two elements, if they are similar or not similar, if they belong or not to the same cluster, how can I decide this? You must say, for example, before it was Cole, I think, or Ayub, one in this table, in all cases. Someone told me we measure the distance to the centroid, or it was Jerry. It was.
With pixel.
Yeah, you are right. So in this case, the measure that you are deciding to decide this is similar to this or not, I'm going to use some distance, and I'm going to measure. To measure the distance between two images, Ayub is saying that we measure the distance between each pixel in that image. Okay, if we do this, we can find this lady in the same category with this dog, and this one in the same category of this dog. So this is highlighting a very important point, which is the choice of the similarity metric, which is extremely important. Okay, so the distance, it could be used to measure the similarity or the dissimilarity, but it's like subjective, like we say. And when we talk about distance also, there is many types of distance, okay? So, and what we say, what distance you know the most or you use the most? It is Euclidean distance, because whenever I may ask anyone, everyone knows the Euclidean distance. But what we really don't know, or we need to highlight, that the Euclidean distance is a particular case of the distance of Minkowski, which is given now I have two, I'm going to say it cluster, okay? Because this is X, this is given the attributes for this given by the vector x1 to xn, and for the shape or element or like sample y, I have attributes from y1 to yn, okay? So what we have, we are measuring the distance between this x and y, which is corresponding to measuring the distance between each element, each pixel, like Ayub was saying, or each attribute of these elements, okay? Pixel if it's an image for sure. Okay, so the distance here is given by this formula, which is quite similar to the Euclidean case. So here we have the sum of the absolute value of the difference between the attributes of x for a given like order, like for example 1, 2, 3 minus the I, okay, minus those of y. For example, the first one, we are going to divide the second one, the first one for y, the second y for x from the second y for y, the n1 for x from the n1 for y. Is that clear? So we can see here there is like power 1 over p, and there is here 1p, and this is the dp. So p, what makes the difference between all subtypes of distance. So when this p is equal to 1, it is the Manhattan distance. We have seen the Manhattan distance, but we didn't see the formula. So this is the Manhattan distance. It's when you are performing the difference between the attributes of y, x minus those of y, for each one for sure, with respect to the order for sure, and you are having the absolute value, you are summing all of that together, okay? So this is the Manhattan distance. If now you are going to give the value of p going to increase with 1, which is p equal to 2. So here, how can you imagine this formula? So this is called the d1. So here we will have the d2, which is going to have, you are right, so it's the square, because when we have 1 over 2 or half, which is could be written as a square, okay? With the same thing here, and here we have power 2 because our p value is equal to 2. And this is the famous Euclidean distance, okay? Now, if you are going to have your p up to infinity, which is more representative to the reality, and in this case, how can you imagine this formula?
Does this approach 1?
Yeah, okay.
Okay.
So how to write in the formula, this p is going to up to infinity. So if you are summing up to infinity, it's like you are assimilating to the max, okay? And so it's always the difference between these two. Now, how to represent this? We are coming to the point of Jeremy. If we are having, so now we are done. So this is the L1, L2, and this is the L infinity norms, okay? So the number 1 is the Manhattan distance. So if you imagine this formula in this space, how it could be looking like? This is what? Which one is this? So if you have a point and the distance, it's always the same, which at the end, the set of points is equal to 1, which is giving the L2. L2, which is the Euclidean distance. We know this. Now, the Manhattan distance is given by this one. If you imagine, I'm going, because if this point is far from the center 0, 0, this distance is the Manhattan distance. However, if I want to check where is that point which is far from that same point with respect to the Euclidean distance, it is this one, okay? Now, if I imagine it with the max distance, it's going to be, and Jeremy was right, it is V square. So, which means that having different formulas for the different distances is translated by having different representations for each like point distance to the center of a given axis, for example. It's different for each case. And the choice of this distance now, if I'm going to measure whether using the Euclidean or Manhattan or the max distance, it depends upon on the use case. There are some use cases when if I apply the Manhattan distance, that is the best option. And this is what we see in the case of our search problems. In the first chapter, we were using the Manhattan distance. Remember that? Okay, another example. So when, for example, we go for this, if I want to travel from USA to France, let's say, as a first step. So from USA to France, I'm going to ask you about the distance. What are you going to say? The distance, okay. But this is USA. And this is, let's suppose, France. So how can you measure the distance between these two like countries? Can never be the Euclidean distance. It's not like we're bringing 1 meter and we are checking the distance. It's impossible. So if you are like in a plane and you are checking the distance to the destination, for example, it's going to show you not a straight line between both elements, not a straight line, because the straight line represents the Euclidean distance in general. So what you see, it's an arrow, which is like this in general. And it's saying to you how long it's left, for example. So this shows what? Not the Euclidean distance. It's a particular case of the Manhattan distance. Sometimes we use distance with respect to the geometry where we are. So France or USA, they are both on Earth. And how it's the shape of Earth. It's not like if I am having my plane from X1, I'm going to make like X1 minus X2 is within the same plane, which is a surface. It's a 2D space, okay? However, in this case, I have sometimes water. I'm going sometimes through some forests. There is sometimes a tree. So there is a special geodesy, I'm going to call, for this particular case. So the distance that respects the geodesy of the like Earth, like for example, you are camping and there is like, you are going here. How do you measure the distance from this point to this point? It's not the straight distance, straight line you are going. No, it is like you are going to measure, I'm going to say your steps, for example, from here to here. And you are going to check, for example, the different steps to reach here. So when I'm saying steps, it's like if you are going in the up direction, you are respecting that geodesy. If you are at some convex point, you are also respecting that. So the distance that respects this, like it's kind of Manhattan distance or a distance that you will call it geodesic distance, okay? So there are different types of distance. There are different types of measurements. So how to use this? It's up to the context. So this is one, the L infinity. Now we are still in the case of nominal attributes. And if we can compute the distance, we can compute it between numerical values, like between pixel values, for example. So now what we have, we do not only have that, we can have other types. We see for new one, for example, like nominal attributes. And if I want to compute the distance in this case, there is a different formula. We are defining this. but it's not the Manhattan distance, it's not the Euclidean distance, it's not the distance, the infinity distance, no, the max distance. It is the distance between two like vectors x and y, such as that these vectors are going to have like nominal attributes, which means that from x1 to xn and from y1 to 1n, they belong to omega, which represents nominal attributes, okay? In this case, what we will do, the distance is n minus q divided by n, where n here is how many elements we do have. For example, from 1 to n, if your n is 5, it means you have 5 elements. So you have 5 minus q divided by 5. So what is this q? It is the number of attributes with the same modality in x and y, which are things that are unchanged, okay? Let's take an example. Or let's define this particular case or particular type before that. So there is a particular case of the nominal attributes, which is the binary nominal attributes. And in this case, what we do use, it's not the distance, we use the coefficient matrix, because we are sure and we know that for each element, there is only 2 possible values, like the truth table we have seen so far. So if I have one attribute, it could be whether 1 or 0, okay? It could be whether 0 or 1. So I'm going to represent my attributes, and I'm going to give, for example, here A, which is attributes that are taking 1, 1, 1 for x and 1 for y. B are those taking 1 for x, 0 for y. C are those who are taking 0 for x, 1 for y. And D are those who are taking 0 for x and 0 for y. Okay, so this is a way to represent it. So if I'm having a matrix and it's representing like values, which is numerical values, A is the number of something, which is going to be translated with a numerical value. So this matrix is going to represent quantitative representation of whatever in the start is a qualitative, okay? So let's see first case or example of where we are having symmetric binary attributes, which here in this case we are giving to have the same importance for both 1 and 0. And this is called a simple matching coefficient, okay? So distance here is going to be the B plus C, and to see B plus C is elements with the having different 1, 0 or 0, 1. It's not those who are on the diagonal that are 1, 1 or 0, 0. I'm going to divide that by A plus B plus C plus D, which is the whole thing, okay? So in this case, let's measure now the distance between this X having these attributes and this Y having these attributes. How to do this?
It's just a ratio of the number that are different over the total
Yeah.
number, right?
Yeah, so how to do that? How many for each one? Let's
Should-
calculate that. So 1, 1, which is same for X and Y. How many? 1, 2, okay? It's not changing, it's the same. A, which is double 1, which is only 2, okay. Then the double 0, which is D,
There's 2 Ds as well.
okay. And C, which is 0, 1. So we keep counting with this concept, okay? Now, what we'll give 2 plus 1 divided by 2 plus 2 plus 1 plus 2, which is going to give this value. So here you can see you are checking the distance between these two like feature vectors or these two set of attributes. Even that, you would say, how is it possible to measure this type of distance? So in this case, what you are using, keep in mind, it's called the simple matching coefficient, which gives the same importance for 0 and 1. However, there is a different way of doing the same thing, which is using the Jaccard coefficient, which is going to consider that 1 is having more importance than 0, okay? And these metrics are already existing. So the formula this time is going to sum the B plus C and divide that with only A, B, and C, okay? We are excluding this D because we are only considering that the ones with having 1, 1, it's more important than 0, 0, okay? So in this case, we do the same. Like how many elements are 1, 1, for example, like you're just saying it's 2 plus the 1, 0, and so on. So you are going to have it 1. So 2 plus 1 divided by this. What we did is just we are excluding the 0 part, okay? So this is going to give, let me say, more accurate, like it depends open from the context for sure, which is going to be 3 over 5. So all this is useful when we are talking about k-means because this algorithm, as the name mentions, it computes the means. And if we want to compute the mean, it means that we need to have a particular distance. We are based on a particular like computation. So here we need to have knowledge about which distance to use, which is depending upon from what input type we have. So the type of distance, subjective as well, because we, as we said in the start, how many clusters we can form given the Simpson family. Some of you say 2, some of you say 3. So it depends upon from the context, the choice of how many groups we are going to form, okay? So it's a 4-step algo. So the first step is to initialize, to choose. I'm going to divide this group into 2 elements or 3 like subgroups. I'm going to say clusters means how many, because there is no rule, and I'm going to say there is no rule that give you the correct final number of clusters. And this is how we started by saying that clustering is subjective, okay? But we will see later in the state of the art how we did to solve this, okay? There is a set of suggestions, but I won't call them rules, okay? Let's suppose we are dividing the space into 2 groups, 2 clusters, 3 clusters, 4 clusters. So the first step is to decide about K. The second step is to assign first and then reassign each object O to the cluster Ci with the center Mi, such that the distance between the center and the object is minimized. And we are going to recalculate this like center Mi for each cluster, the centroid, because as I was saying, it's not fixed. It keeps updating its position until the end. It's going to converge. We're going to repeat steps like 2 and 3 as many times as until convergence, okay? So this is an illustration of the k-means algorithm. If I have this example, how many, the first step is to take, it's to decide about K, how many clusters I have. For example, K is equal to 3, okay? Now, or K is equal to 2, it depends, or K is equal to 1. There is no rule for this, and this one of the inconvenience of this algorithm. Then I'm going to initialize the centroid positions, like for example, I'm deciding, or the red one is going to be here, green one is going to be here. So blue one is going to be here, it's 3. And the position in the start is just random, okay? And next, what we are going to do is we are going to assign, for each element, we are going to compute the distance from the centroid, and we are going to say these are near to this one, so they are assigned to this one. Then these are near to this green one, then they are assigned to it, and these are near to the blue, and so on, okay? We are assigning. What to do later? It's like we are going to recalculate the position of the centroids using the average each time, and this is going, you see here, the centroid is moving because there is more population, I'm going to say there, and this one, then it's not, it's going to be affected to the other group, okay? So I keep doing this and repeat it until the centroids do not move anymore, and at the end, they're going to have a fixed position, which is translated by a convergence, okay? So this is the final like case. What is the stopping criteria for the k-means? There is no more changes in the assignments of shapes, like that we understand that it needs to stop. There is no more changes in the position of centroids, and like that and we understand the same. And there is a stabilization of the decrease of the sum of squared error, because if you remember last time, we said we measure the performance given some metrics. One of the metrics is the error. And for error, there are a set of like equations. This is one of them. I'm going to say the very simple one, which is the square error. And the square error, as you see here, it's like power 2, the distance between m and g, and it's the double sum, okay? So this is the criteria, and for the optimization part. The advantages of this algorithm is that it's easy to implement. It is having a low time consumption of the order of t times k times n. And the bad things or the disadvantage of this is like the hardest thing is to decide about how many clusters I'm going to have. Okay? The thing is that it's empirical, this choice of k. So this is the hardest part. Next, keep this in mind, we'll come back to this. We need numerical attributes to calculate the mean for symbolic attributes. Means it's replaced by the most frequent attribute, which is just an attempt to, but it could not be that much accurate in some cases, okay? There is poor handling of outliers. If you remember before, when we see that this line separating the blue plus from the red circles, you see, I told you, see here, there are some red circles which are still in the surface, which is related to the blue ones. So these are called outliers. Outliers, it's like you have an, what we say, what example of outlier, for example?
Like a chair with two legs?
For example, or that story. The duck, which is black, and the others are all yellow. So
Right.
it's belonging to the same category, but it's having different color, for example. Okay? Or if I had a student 2 years back, I used to call him Ferrari because I feel like he knows everything. So I call him, okay, this is the outlier. I don't teach him. I need to have separate classes with him. Otherwise, we do not consider the outlier. All the time I say that. So outlier is someone which is like particular case, okay? And we need to treat all the time with particular like way. So we are almost done. Last point, which is extreme points outside the groups. Okay, so for example, you have some elements that could distort the mean, okay? Because if they have extreme values, they can have impact on the mean, and this is k-means. It's based on the mean computation. So we come back to the first point about the empirical choice of the number of groups. As there is, this point is a negative point, let's say. There must be researchers or people who are finding methods or introducing methods how to choose the best number of k, okay? And now I would maybe let you ChatGPT it. I won't say Google it. ChatGPT it and check. I did that, by the way. What methods for choosing the number of groups k in k-means clustering? So if someone is going to say there is one method, and in general, when we teach this, we study one of the methods, which is, for example, the elbow method. Say in elbow, it's like the hand, and the elbow method is given point of k where I understand. So I have a population, I have points. I'm going to suppose k is equal to 1. I'm running my algorithm. K is equal to 2, running my algorithm. K is equal to 3, running my algorithm. So I'm going to have at the end the representation where I find a big change, like in the elbow, like this. I'm going to say, oh, this k means something, which is the best k, okay? It's not only that, and I'm against teaching only the elbow method when it comes to the k-means. There is a set of other algorithms. There is the silhouette score. There is the gap static. There is the Davis-Baldwin index. There's cross-validation. There's domain knowledge. So each one of these, it's a method. It's like some research coming with a method that's saying this is the best method to decide about your k. But at the end, okay, you can, if you are in a clustering problem, you can use, I always recommend using the elbow method, okay? But you need to keep that it's just one of the existing methods. By yourself, you can introduce a new method. And at the end, the main disadvantage of the k-means is how to decide the number of groups. It's a huge problem in science. So I think first time we are on time. So that is it for today. If you have any question, please let me know.
No, but this explained quite a bit. I really liked that visual of having those centroids move around.
Thank you so much. Okay, so that is it for today. See you.